Welcome to this session on embedded systems. We are very honored to have Professor Manoj Choudhary with us as an invited speaker. Professor Manoj is currently working as a professor at IIT Jodhpur, and he had leading positions with top multinationals like Samsung and Texas Instruments for 20 years before moving to academia. He is known as a pioneer of wireless standard activities in India and has led standard bodies worldwide. Professor Manoj has delivered numerous papers, talks, and tutorials in national and international conferences and industry forums, and has over 30 granted patents. Professor Manoj is a senior member of the IEEE and also a distinguished lecturer at IEEE Communication Society. We are very honored to have him with us as an invited speaker today, and he will talk about AIoT-based systems. The floor is yours.
Good afternoon, everyone. It is my pleasure to be here at the VLSI conference and to be able to present on AIoT-based systems. Let me share my screen and get started. Are you able to see my screen?
I see your screen, but it's not in, yes, now it is in presentation mode, yes.
Okay, so I am presenting on AIoT-based systems, that is artificial intelligence of things based systems. So the background of this is that, as we know, IoT is rapidly evolving and getting deployed right from smart home to smart city to smart globe. And it is playing a vital role in connecting devices together, making devices more smarter and allowing connected devices to leverage the power of internet and wireless. However, the way IoT will impact further going forward, because each of the device connected in IoT ecosystem generates a lot of data. Therefore, ability to handle data in a timely and effective manner will determine how much we can utilize the benefits of IoT. On the other hand, recent advances in AI, artificial intelligence, have brought in opportunities that can overcome the challenges of IoT development, in the sense the lot of data that IoT devices are generating. AI processing can actually help making sense of the data and to create recommendations for that. Therefore, integration of AI and IoT technologies becoming a very promising trend to promote evolution of the whole IoT ecosystem. Now, is AIoT what we call artificial intelligence of things? Is that simply AI plus IoT? It is not so, but it adopts technologies such as AI and IoT, which is supported by big data, computing, using semiconductors as algorithm carriers, network security technologies as implementation guarantees, and 5G as one of the catalysts that can integrate data, knowledge, and intelligence. Therefore, AIoT is leading to thinking networks and systems that are becoming more increasingly capable of solving wide range of problems across agriculture, smart transportation, factories of the future, healthcare, and so on and so forth. In this whole context, what AI does to IoT is AI adds value to IoT through machine learning and improved decision making, whereas IoT adds value to AI through communication, connectivity, signaling, and data exchange. AIoT as a whole, as a system that we are trying to develop, is the one that will realize dataization of all things and intelligentization of everything. Therefore, it applies intelligence on the edge and gives devices the ability to understand data, observe environment around them, and decide what to do best. With the power of AI, IoT devices are no longer messengers that just feed information to the control center, but have evolved into intelligent machines. For example, if you have a smart appliance at the home, they not only work based on instructions that you are giving through your smartphone before you arrive at home and so on, but appliances can become smarter by sensing the surroundings, and therefore, using that kind of a function, they can become even more smart and take informed decisions. Therefore, AIoT offers unique opportunity to modern society through personalized services, tailored content, improved availability, accessibility, and cost-effective delivery. Going further, here what we try to do is that we embed AI into the infrastructure components such as program, chipset, and edge devices, all interconnected AIoT networks. We use APIs to extend interoperability between the connected devices, device level, software level, and the platform level. These units primarily focus on optimizing the network operations and extracting value from the data. Many cases, data itself can be a service. Many cases, it is actionable information that is a service. The whole infrastructure of artificial intelligence of things, AIoT, will in future create a foundation for IoT data as a service and AI-based decisions as a service. In terms of market, without getting too much into that, all I can mention based on various sources through the secondary research, the data that growing AIoT market is growing at a 39% compounded aggregate growth rate. Therefore, a huge opportunity is coming our way, leveraging both AI and IoT devices together with applications areas that I briefly mentioned, primarily for automating processes, providing predictive and advanced analytics, business insights, and improving customer experience. Therefore, across a range of industries, starting with smart manufacturing, healthcare, smart infrastructure, energy grids. These days, when we have energy grids where renewable energy sources like solar and wind are also integrated to energy systems. So how do we stabilize and have a predictive energy grid system? Therefore, AIoT devices and multitude of sensors that are located there actually can help greatly in such kind of missions. Traditionally, we performed AI computations. They were performed at a separate level, not at the device level, in the center in the cloud. With the implementation of many AI models that are these days happening within SoCs like GPUs, NPUs, and so on, important shift has already occurred from cloud level to a device level processing of these artificial intelligence tasks, data, and results. Therefore, embedding this AI is one of the important applications of machine learning and deep learning in software and the device level. There are two different approaches that are evolving. One is embed AI capability as a custom SoCs, leveraging and optimizing chips architecture, thereby reducing instruction counts, power consumption calculation for specific types of actions that we need to perform, or have AI that is embedded into the internet connected devices itself in the IoT world. This is a very simple diagram, basically just shows how the intelligence can be distributed for an application based on blockchain, right from cloud to a fog nodes, and how can we bring the intelligence right to the device level and at the edge level when we deploy 5G and try to utilize a structure. Going forward, most of the AI devices, as we know, work very strongly on perceiving, learning, behaving, and the action that we take, the reasoning that we do. This example here only shows perceiving systems. There are a multitude of aspects. For example, object detection or scene understanding. These are some of the aspects of perceiving systems. In learning systems, there are many reinforcement methods of federated learning schemes. In terms of reasoning, there are whether knowledge graphs or causal approaches can be used. In terms of action, you can have a control or an interaction method. There are different methods that one can use based on application type, whether it is smart healthcare or for transportation and so on. Multitude of AIoT applications are listed here. In terms of technology areas, there are progress that are happening in sensor, communication, computing, AI, ML, of course, and the applications these days where we are trying to make a smart factory in Industry 4.0 scenario. How do we utilize various sensors and the device data that generated from the sensors to make these factory operations more efficient, operated at optimized capacity, and so on. Similarly, the case for energy grid, I already talked about that. Healthcare for predictive analytics is becoming very important. Agriculture, for example, depending upon the humidity levels and the current level in the soil, what can these AIoT devices that are installed or put in the agriculture space can significantly improve the quality of life as well as the quality of operations. There are many research challenges currently in AIoT systems. This is my last slide before I talk more about briefly about what we are going to do at IIT Jodhpur. In research challenges, as we know, we are trying to have the AI functions more in the edge devices that are deployed in the IoT scenario. Therefore, situation and intention awareness is very important part. So is if there are multitude and billions of such sensors are getting connected, how do we ensure that they collaborate amongst each other for a communication? How do we have IoT operation and maintenance through AI enabled? We develop many simulation tools, methodologies, and performance evaluations, and many approaches to the intelligent transportation systems, for example, smart traffic lighting for the smart city operation or home or healthcare in the grid. What we are trying to do is briefly, I wanted to mention at IIT Jodhpur, we are setting up the AIoT Innovation Hub, for which a foundation stone was laid by the Vice President of India 3 or 4 months before. This AIoT Innovation Hub will not only do a research and R&D in many areas that we mentioned, but is currently poised to work with industry partners to develop solutions that can be used as an end system. And therefore, through this conference, I solicit participation and collaboration from all the partners. In IIT Jodhpur, apart from traditional departments, we have a very strong school of AI and data science, and we are developing an ecosystem with various ecosystems related on AR/VR. We have an All India Institute of Medical Science here in Jodhpur, with whom we are tied up for many of the medical and the connected healthcare segment. Many of the AIoT applications for connected healthcare, for example, is happening there. And in terms of the Center of Renewable Energy, many aspects for AIoT that are being used for energy grids are being discussed here. So I know our session started late, and therefore I would like to stop here. If there are any questions, I'll be happy to take. Thank you so much for listening to me.
Thank you so much for the very interesting talk. If I am not mistaken, there are no questions in the chat. But to kick it off, I have a question actually to you. Yes. So you mentioned many research challenges, and one of them was security. But to enable secure communication, energy hungry and computation intensive algorithms are needed. How do you see the future for that? Do you see it possible in the near future to have those very complex algorithms on IoT nodes?
So these days, even in the hardware, there are many provisions for security. However, there are many aspects like hardware trojans, for example, that are one of the important issues in many of the hardware that we are facilitating and putting at the device edge, or the lightweight security processes that will result into a trust-based computing that, for example, is an underlying architecture for a blockchain and so on. So many lightweight, scared, and layered architecture, even in the security and through many standards that are currently deployed in IEEE, 3GPP, and so on, for security level paradigms in these AIoT-based devices is something that is going to be very, very critical as we go ahead. So thank you for a very good question. Thank you.
Okay, thank you very much. If there are no further questions, then I would like to thank you very much again. It was a great talk, and thanks for giving us the honor to have you as an invited speaker.
Thank you. Thank you so much, all of you. And let's move to the next part of the embedded systems track. Thank you.
Yes, indeed. Thank you very much. So we have two more talks of accepted papers at the conference, and the first one will be on a PC-based ultrasound backend signal processor using Intel performance primitives. And the authors are Jayaraj Kidav, Sreerama Pavan, Rajesh M, and Navinkumar W. So the floor is yours to the speaker.
Good morning to all. This is Sreerama Pavan. Now I am presenting a video on our paper, a PC-based ultrasound backend signal processing using Intel IPPs. The co-authors for this paper are Sri Jayaraj Kidav, Sri Rajesh M, Sri Navinkumar W. We all are working in the NIELIT Calicut Center, which is under Ministry of Electronics and Information Technology, India. Now I am going to discuss about introduction to ultrasound imaging. Then we will see about the PC-based ultrasound backend processing and display. And then we will see about ultrasound backend implementation using Intel IPPs for the modes B mode, M mode, and spectral Doppler mode. And then we will see about the result, which will compare the processing time for these modes using Intel IPPs and using conventional C programming. And then we will come to the conclusion, and then we will see the references. Coming to the introduction part, ultrasound imaging is a non-invasive diagnostic techniques. Here the transmitter transmits short bursts of high frequency acoustic signals, and then the transducer channels have captured the reflected signals. That means the echo signals has been captured by the transducer channels, and then it will transmit to front-end processing for doing the beamforming techniques to generate the scan lines. Here we are using conventional delay and some beamforming technique. Typically, two-dimensional image consists of 50 to few tons of scan lines. Scan lines data is processed in backend using PC for the resultant modes which we have selected in the GUI. Now this is ultrasound B mode, M mode or spectral Doppler mode image acquisition block diagram. The transducer, it captures the reflected signals and then it will send for front-end image processing to generate the beamformer data, and then that data has been transferred to PC for back-end signal processing. Here we are transferring using Ethernet based. Using Ethernet we are transferring the data from that beamformer data from FPGA to PC. So in the PC, the back-end processing blocks are for identifying the amplitude of the signal, that RF data, using envelope detection, and then we will do the log compression, and then we will save in the buffer, which is frame data, which is refreshed periodically. And then based upon the selected modes in the GUI, that frame data which is saved in the buffer, it is fetched, and then it will generate the beam mode or M mode or spectral Doppler mode on the two-dimensional display. Now ultrasound implementation using Intel IPPs. Here we are going to discuss about the modes: beam mode, which is also called as brightness mode, and M mode, which is also called as motion mode, and then about spectral Doppler mode, which is also called as SD mode. And before going to discuss about the beam modes, I am going to tell about the Intel IPPs. Intel IPPs are Intel Integrated Performance Primitives, which are extensive library of ready-to-use domain-specific functions highly optimized for Intel architectures. Intel IPPs support signal processing, image processing, and three-dimensional data processing with different data types. It utilizes various cores to perform tasks in parallel such that execution time has been reduced. Ultrasound backend implementation using Intel IPP for beam mode imaging. The beamformer data has been sent in the backend processing for extraction of amplitudes, that is the envelope detection. This extraction of amplitude has been identified using the by generating the analytical signal. The analytical signal has been generated using the help of Intel IPP's function IPPS Hilbert _ 32F 32FC function, and then the magnitude of the analytical signal has been found using the Intel IPP's function Intel IPPS magnitude _ 32FC function, then which results the amplitude of the scan lines. Then it has been sent to the log compression block for removing the dynamic ranges of the signal. This has been accomplished using the function IPPS log to the base 10 _ 32F _ A21. Here A21 will tell us about the precision of the output signal. That 32F is the data type of the signal. And then we are sending to the scan conversion for the field of view. Here we are converting into the 8-bit unsigned integer for grayscale imaging. This we can be accomplished using Intel IPP function IPPI convert _ 32F 8U _ C1R function. Then we are transmitting for the two-dimensional imaging in the GUI, which will look like this. Here we have captured the phantom data and then we are displayed. Ultrasound backend implementation using Intel IPPs for M mode image. In the M mode image is a combination of B mode image and a continuous A mode buffer data. This scanline selection and for M mode image is necessary to display in which scanline data, continuous A mode data we want to display. These functions, the functions which can be used for accomplishing these tasks are similar to the B mode image functions. Here in case of M mode image, we are taking that beamformer data and then we are sending to the envelope detection, then log compression, then scan conversion, which is the B mode image, and that after the long compression data which is saved in the buffer, that data based upon my scan line selection. I am continuously fetching that particular scan line data and saved in the buffer, and then similar to beam mode image, here also I am doing the scan conversion and then I am displaying in the 2D image, which will look like this in the GUI. Here in the M mode, this scan number slider which will tell us about the which scan line I want to display in the M mode. Okay, here this slider in the beam mode image, it will on the picture it will represent which scan line we have selected, in which area of scan line we have selected. In the second image, that yellow colored circle, in that one it represents that M mode data, which is continuous M mode buffer data which is displayed. Ultrasound backend implementation using Intel IPPs for spectral Doppler mode. Here in spectral Doppler mode, in addition to beam mode, we are displaying the spectrum. For this, we are selecting in which scan line you want to display the spectrum, and in that particular scan line what is the area you want to consider. We are selecting that area, and for that area the data has been taken, and then we are doing the Fourier transform, and then the resultant data has been scan converted, and then we are displaying on the two-dimensional image. So the functions we have used for generation of this spectrum are IPPS FIR SR function and then IPPS FFT FWD function. In case of conventional C programming, for generating the fast Fourier transform, we are using FFTW library. Here this is the display of the GUI. Here where and all we are selecting, there I have circled using the yellow color border. Here in the SD mode, we are selecting the scan line number using the slider, and in the when we have selected this scan line number, in my beam mode image it is one cursor has come, and in the slider there is one dash lines are there which will select the area of my interest for the spectrum, which you can observe using that first yellow rectangle. And in the second image, the spectrum has been displayed and it is highlighted using the yellow colored rectangle. And coming to the result, the average time taken for implementation using Intel IPPs and using conventional C or C++ program for 6 consecutive frames has been taken, and it is tabulated. For the ultrasound image mode, only beam mode image using Intel IPPs, it took around 16 milliseconds. This is the average time for 6 consecutive frames. Using conventional C and C++ program, it took around 29 milliseconds. In case of M mode image, which is a combination of beam mode and continuous A mode buffer data display, using Intel IPPs, it took around 15.5 milliseconds. Using C or C++, it took around 30.5 milliseconds. In case of spectral Doppler mode, that means using beam mode plus spectral Doppler mode, it took using Intel IPPs, it took around 14.5 milliseconds. Using conventional C or C++, it took around 32.16 milliseconds. So by observing this, for the ultrasound imaging frame rate using Intel IPPs, the maximum frame rate we can generate is 64 frames per second. If we are using conventional C or C++, we can generate 31 frames per second. By comparing this one, we can observe that using Intel IPPs, we can generate the more frame data. Coming to the conclusion, the performance of ultrasound B mode, M mode and spectral Doppler modes using IPPs and conventional C or C++ are compared and tabulated, and the results shows that the implementation of backend signal processing using Intel IPPs increases the speed of execution. So, which is compared to the conventional C or C++. Intel IPP based backend processing implementation yields for the ultrasound system for futuristic techniques like color flow imaging and three-dimensional imaging with a higher frame rate. And these are the references. Thank you to all.
Okay. Thank you very much for the presentation. I was informed that, so normally we would have Q&A now for this presentation, but I was informed that the authors of this paper are not present in the session. So we move on to the next and last presentation in this session, which is Power and Energy Safe Real-Time Multi-Core Task Scheduling by Kalyan Baital, Amlan Chakrabarti, Biswadeep Chatterjee, Stefan Holst, and Xiaoqing Wen. Please go ahead.
Good morning, all of you. My name is Kalyan Baital, working as a senior scientist in National Institute of Electronics and Information Technology, Kolkata Center. On behalf of all the authors, I am presenting our paper, Power and Energy Safe Real-Time Multi-Core Task Scheduling. So these are the outline of our paper. What is the motivation of our work? What are the objectives, main contribution, and the limitation of the existing work? What is the problem statement, novelty of the work, then our proposed model, then methods and approaches, then experimental design, and conclusion. So what is the motivation? So nowadays, real-time systems are employed in variety of applications, and their functional complexities are constantly expanding. So energy efficient and power efficient design of such system is becoming a significant design feature. So scheduling tasks in multi-core real-time system while keeping energy in mind is a difficult design challenge. So extensive work has been done to overcome this issue, in which task instances have varying level of varying level of operating power. So different combination of system energy and subsequent minimum system energy have been achieved with these existing works. However, we know that system power and system energy both are expensive to operate. So a task scheduling for multi-core system based on balancing both the SP and AC is required to achieve the lowest system cost, and this is not addressed adequately in the existing literature. And the balancing of SP and SP are referred to as the feasible SP and feasible AC. So feasible SP and feasible AC is such state or zone where system power configuration provides the lowered system energy with increased job accommodation and thus lowering the system cost. So now with this motivation, our objective is to propose a scheduling approach to identify numerous feasible system power and feasible system zones to fit all the jobs to code, while at the same time minimizing the system cost, including the optimum cost, and maintaining the deadline. So now what are the main contribution? The main contribution is to identify the upper bound and lower bound of several feasible system power and feasible system zone. And next, the system power and system energy are controlled by the scheduler according to the system requirement. And next, to identify the optimum feasible system power and feasible system zone among all the feasible system power and feasible system zone. And finally, we find a ranking of the feasible system state with respect to system power and system energy. So there are several research works are there, but they but they have certain limitation. For example, work 2 addresses a compressed cache to improve energy of cache compression, but it do not address the overhead issue and do not address the issue of balancing the power and energy. So, for example, work 3 provided a strategies for heterogeneous multi-core system to improve the energy efficiency, but this paper also do not address balancing the parameters to get feasible zones of the system. So I am not going to the details of these existing works. So there are a lot of existing works who addresses several issues to minimize the energy of the real-time system, but the lack of addressing overhead issue, balancing both the power and energy, and also do not address the cost of the system. So there is a necessity for scheduling model for allocating job to real-time system such a way that system energy and power are balanced to increase both the cost efficiency. So our work presents a scheduling that includes both SP, feasible system power, and feasible system energy to handle all tasks considering all the parameters, namely energy, power, overhead, and cost to get the feasible zone of the system. So before going to the problem definition, there are certain terminologies. First one is the cost effective. So any state or zone of the system which is termed as the feasible zones can be called as a cost effective state or zone where the power configuration produces a decreased system energy with the increase of system power. So varying system energy with the increase of system power in the multi-core system has also been discussed in the existing literature. Next terminology is that power and energy budget. So total power and energy consumed by a system for the accommodation of all the tasks is called power and energy budgets. And the power and energy save is the state where the system is cost effective and balanced in terms of power and energy. Now, what is the problem statement? A set of periodic low power tasks with respective deadlines and execution time has been given as input. And the tasks have a particular number of power level of operation, which is defined by the frequency. Now we have to find the feasible system powers and feasible system energies such that total power and energy of the system produce a cost-effective solution. Next, we formulate a ranking. We have to formulate a ranking with these different feasible zones with different feasible zone, and finally from this ranking table we have to select a particular feasible system power and feasible system energy to make the system a power and energy save in terms of cost effective and in terms of balancing the power and energy as per the requirement of the user. So what is the novelty of the work? That is, we know that there is a trade-off between power level and the execution time. So, and different combination of power levels and execution time consume different system energy. So system energy may be increased or decreased with the increase of power level because execution time decreases with the increase of power level, and the multiplication of system power and execution time may be increased, which produces the system energy, and this system energy may be increased or decreased from the previous one because multiplication of the power level and execution time may increase or decrease from the previous one. So now consider the three cases where the tasks are being operated in three power level of operation. First one is the lowest frequency, which produces lowest power level, but deadline of the majority of the tasks will not be met in this state. And the second type in the second types of power level, frequency is greater than the lowest frequency to meet the task deadline. And the third case is that highest frequency tasks meet the deadline, but here the highest frequency level produce the highest power level. So we can imagine that case 1 and case 3 is not a feasible solution at all, because they do not produce the optimum result for the system. So now the case 2 is the feasible solution, where we can find different feasible system power and corresponding feasible system energy, and where system energy decreases with the increase of system power to have a cost-effective solution. So it is a challenge to find such feasible system power and feasible system energy from the case 2. Now our focus is to find that upper bound and lower bound of feasible system power and feasible system energy from this case 2, that is from this power level, which is higher than the lowest power level and lesser than the highest power level. So now our problem model is that we have several power level W1, W2 up to N, and there are several execution time of tasks based on the power level, and we also have the release time Rij and deadline Dij corresponding to each task, and the tasks and the power level of the tasks consume energy F1, F2 up to Fn, and we define a formula F equal to W into E, where W is the power level, E is the execution time, and we get the energy by multiplying of these two. And job execution time corresponding to each power level are found from existing benchmark and with the help of geometric mean formula. So with this power level and execution time, first job are assigned to local queue of matching code based on a particular power level, and in the local queue, jobs are allowed to be switched among different power level of operation, and we get different possible combination of system energy, and finally we incorporate the parameter of feasible system zone, feasible system power and feasible system energy to this model to get the feasible zones. So this is the problem model which is based on our existing work. Next, what is our method? We calculate all possible system energy considering the combination of job execution time and corresponding power level using the formula O1. Then we also find all the system power. Then based on the system power and system energy, we plot the graph and we find the feasible system power and feasible system zone from this plot. And then we find a ranking of the system performance considering a weighted average of the power and energy budget with the formula as defined in 3, where W1 is the weight given to the power and W2 is the weight given to the energy. We assume here that 30% weight has been given to power and 70% weight is given to energy. So this ranking may be changed depending upon the weight. For example, it may be changed if we give 40% weight to the power and 60% weight to the energy. So this ranking is a proposal to show how the user can rank different feasible system state. So now experimental design and verification. Our approach was tested using a simulation software written in C, real-time activities with different execution time and deadlines are taken as input to the software, and the program's findings were plotted in a graph to illustrate the simulation result. And we conducted experiment on variety of activities, including the task set of existing work 1, and filtered the viable system state from all the successful combination where the system energy are minimized with the growth of system power to schedule the largest number of tasks. So we find the experimental result, and we find system energy ranging from 16.350 joules to 16.750 joule using the formula 1, and corresponding system power is ranging from 6.869 kilowatt to 7.975 kilowatt for the example set of tasks. And the ratio of different system energy corresponding to ratio of different system power is shown in figure 1. We find different from the figure. We find different feasible zones for selection of system power and system energy to accommodate jobs, and the feasible zones are from B to C, D to E, and F to G. And C is the minimum system energy and minimum system power level. Now we can choose several system power and corresponding system energy from these feasible zones, and the system performance is enhanced in terms of energy and cost efficiency. Next, we assign weights to the SP and corresponding AC and calculate a weighted average of the system using the formula 2 to find a ranking of feasible system state. Based on the ranking, user has the flexibility to choose different power and energy value of the system to construct a particular energy signature. So we find different system energy from 6 joule to 25 joule for different set of tasks with different execution time at different power level. So our model is scalable for low power devices and appliances which produce 6 joule to 25 joule energy, system energy. And we further plot figure 2 to find speed change overhead corresponding to the ratio of different system power. Speed change overhead is occurred due to the switching between different power level. So from the figure, we can see that speed change overhead decreases gradually in the feasible zone, that is from B to C, D to E, and F to G. And optimum speed change overhead zone is F to Z, but optimum zone considering the system power, system energy, and speed change overhead is feasible zone from B to C. So we can conclude our paper that we have proposed a novel scheduling algorithm for multi-core system by considering the feasible system power and feasible system energy to optimize the cost of the system. And we have shown that the feasible zone of system power and system energy also produced a cost-effective solution for the speed change overhead. To the best of our knowledge, no existing work has ever addressed the balancing of both the power and energy to find feasible zones of the system. So finally, we have found a ranking of feasible system state, and the user can choose the system power and the corresponding system energy from this ranking table to accommodate all the tasks as per requirement. Thank you for listening.
Thank you very much for the interesting presentation. If I'm not mistaken, there are no questions from the audience, but I have a few questions to you.
Yes.
So, first question, you said that you used simulation software in C to test your approach. What kind of input can you handle to describe the tasks that are performed on the multi-core system? Are the tasks also in C, or can you handle other types of input?
Madam, actually, the input has been taken from the existing work. So real-time tasks with execution time, with deadline, and execution time at different power level has been taken from existing work. And this parameter has been fed to our C program, and the output has been plotted in a graph to show the result. So this all are based on the real-time tasks that has been taken from the existing work.
Thank you. In the meantime, there's also a question from the audience. So the question is, so these calculations for ranking in multi-core scheduling have to be done on the system itself? Is this overhead of computing considered in the calculation?
No, madam. Actually, this calculation is not done in the system. It is the calculation which a user can compute. Because if a user want to select a particular set of combination that for example in X power of the system, the Y system energy will be generated, and for this combination there are the set of these are the set of jobs that will be accommodated into the system. So this is the user level calculation. So by calculating this kind of calculation, the user can select a particular power level and particular energy combination of a system, and with this energy and power combination there are several jobs that can be accommodated into a system. That calculation can be taken place in the user level. So user can choose any particular power and energy combination to accommodate all the jobs. So it is not done in the system level. It can be done in the system level, but in our paper we have not done in a system level. It is done at a user level.
Okay, thank you. Yeah, in the meantime, if anyone has a question, please post it in the chat. I had one more question.
Yes,
you had a table where you defined weights to the
yes,
SP
madam. Yes.
How did you define, why did you choose these values?
Actually, madam, weight, just I have already informed, weight is a user parameter. So as convenient in our graph plotting, we have taken 30% weight to the power and 70% weight to the energy. But if a user wants to assign 40% weight to the power and 60% weight to the energy, then the table will be little bit changed, because at that time if I choose 30% weight to the power, then it may be that now there is a rank 1. So if I choose the 40% weight to the power value, then it may happen that the rank 1 goes to rank 2. So like that way. So it is a proposal that how a ranking methodology can be taken place. If I choose several parameter in X. So X is a user defined parameter. So X is assigned to power, and 1 minus X into 100% will be assigned to the energy value. So that X is the user defined value.
I see. So it depends on the application, probably.
Yes, depending upon the application.
There's time for one short question still, and there is one in the chat. How can user calculate or select in real time?
No, madam. Actually, user will not calculate. So I have written in the paper that there will be checker who will collect all the information, but the scope of the functionality of the checker has not incorporated in the paper. It will be in our future work.
Okay.
So
thank you very much.
For the convenience of this paper, we have selected as a value, but in the real time it will be collected from a checker. So in the checker work will be done in our later work.
Okay, I see. Thank you very much for the nice presentation and for being here to answer the questions.
Thank you, madam. It is my opportunity to be here. Thank you.